All right, everyone. Welcome back. How is spring break? Got some rest?
What do you mean?
Okay, ready for the final project and of course the exam too. Okay, cool. So today we're gonna finish the remaining part of the ADCs and talk about the DAC, the DAC, digital to analog converter. Before the content, a few announcements. The homework 7 will be due tomorrow at midnight. We give extra days because we realize that a lot of the content is actually about today's lecture, so it doesn't really make sense to do it right after the lecture. The exam 2, it will be this Friday, the same location. Essentially, whichever classroom you sit last time, it will be sitting at the same place. And it will be similar policy to last time. We will release the data sheet 1 day prior, and if any changes needed or any questions you have, raise on Piazza or come to the open office hours, and then we will have the updated data sheet being printed out, and give it to you during the exam. Any questions regarding the exam 2, logistics-wise? The content cover will be until today's lecture. So you don't need to, so there won't be those long questions regarding one of the previous, like the first semester's content, but you should expect them to show up in the multiple choices and maybe some short answers. Any questions regarding the exam 2? Okay, cool. We will have a review lecture this Thursday, so feel free to attend. And we did release 2 of the practice exams already, so if you haven't checked that out, now is a good time to start looking at those, so you can be well prepared for the exam. The project proposal. So all the teams have met with the teaching staff and then have some revisions you got from your current project proposal. I hope everyone is more or less comfortable with what they're working on, or at least clear on what are the goals for your project in order to consider as a good final project. And with the information from the meeting, please update your proposal. Just update a new version with _new, and then upload to the same folder of your team folder. It will be due today. So, yeah. Any questions regarding this? Okay, cool. And after the after the exams, we were starting to do the student presentations. So this part might feel a little bit new to you, but what we want to do is basically you will get assigned on a team basis on your final project team. Each team will get a small topic, usually around a specific peripherals or sensor modules, IMUs or motors or lidar sensors, etc. And then you would do like a introductory lecture to the class, so that you can get your presentation skills practiced, and also you dig into some of the content that will be related to your final project. The topics will be assigned based on the project proposal meetings we have with you. So you should be expecting the topic to be one of the sensor modules or one of the things that you will be using in your own project. We will try to make the groups that introduces the more commonly used sensor or peripherals at the earlier part of the student presentation lecture, like for example IMUs. There are a lot of teams are using that, so you can expect those lectures to be a little bit on the front end. And for less commonly used or more custom peripherals, it will be a little bit on the latter part. And doing before your slot, make sure you sign up with a 30-minute slot with either me or James, and we can sit down with your draft, and then you do a practice run with us, and then we do a round of polish. When you show up on that, you should have roughly the lecture ready. We're not expected to draw the slides together during that time. Any questions? Yeah.
For this introductory lecture, it says a 30-minute slot. Are we expected to take up the entire 30 minutes with our presentation, or will there be time for guests for?
Oh, sorry. Yes, the 30-minute slot is with us. So the actual presentation you do to the class, it would be like about like 12 minutes or so. Yeah. So yeah. Good question. Any other questions? Yeah.
Have the dates already been assigned to the groups?
Not yet. We're still working on the list. Yeah. Any other questions? Yes.
I'm sorry, can you repeat how long the presentation was? I didn't hear it.
The presentation is expected to be around like 12 minutes or so, plus the Q&A, so roughly 15 minutes. You can, yeah, that's the. Any other questions? Okay, perfect. Let's dive into the content. This is the overall outline of the analog signals in embedded systems, ADC and DACs. We pretty much finished we finished most part of the ADCs in the last lecture before the break. We talked about a few different types of ADCs and how they work underneath and what's the trade-off between them. And today, first part, we will be finishing the ADCs, the star ADCs that we have on the microcontrollers you guys use, and then the majority part will be on the DAC, the digital to analog converters. So we already talked about this. These are the amount of ADCs we have on the board, various external channels and also internal channels, and you can set those ADC channels to be different resolution, basically. Tops to be 12-bit. And we also have the analog watchdog per ADC, which is used for mainly like a hardware threshold monitor. We'll talk a little bit about this in more detail later in the slides. So this is actually what the sampling ADC time will look like from the systems perspective. So you actually have a choice of setting how long the sampling time will take, essentially the sample and hold circuit. In the systems, the minimum would be, I believe, 4 cycles, and you can set it to be much longer. And once that value is being sampled, and then it goes to the, as a ADC value. So from like a high level point of view, so this will be how a actual time for sampling and conversion take, or like the whole ADC sampling time takes. It will be containing first part the sampling time and also the conversion time. The conversion time usually is in the perspective of SAR, because it does this binary search, the worst case scenario and all that. You can set it to be just n times the ADC clock. The n meaning how many bits you have for this ADC. So it's a 6-bit ADC, 10-bit ADC, etc. And the sampling time would be actually the thing that you can set here. Different cycles you can assign the hardware to take to do the actual sampling. So any guesses on why we need to, or why it's good to have a configurable sampling time for the ADC channels? Any guesses? So it's mainly just to be more flexible, because chances are the ADC will be connected to various different type of sensor modules or to the real-world signals. And the time it takes for that sensor to become stable on its output can vary. It depends on what's the output resistance that sensor internally has. It could take longer amount of time for the capacitors you put together with the sample and hold circuit to charge up to a point where it's very close to the actual value. So that's why it gives you this configurable methods to set how many cycles you want for each of these sampling. For the sensors that just take maybe in the nanosecond or so to sample, you can select like a shorter amount of cycles to sample. If it's for whatever reason it takes a long time to get stable, then you can use the longer sampling cycles. And to just give you a little bit calculation practice, this will be for the worst case scenario. So if we want to calculate how long it takes for any specific ADC configurations to sample a value, then we have the formula we showed before. The time ADC will equals the time sampling plus the time it takes to conversions. If say we have like a 16 megahertz connected, and sampling time set to be sampling cycles set to be like 4 cycles, and it's a 12-bit ADC, so the time you have will be pretty much 4 plus the 12. And then if we convert that into the actual time, it's that value, so 1 millisecond. And for like a 6-bit ADCs, it would be about like 625 nanoseconds. It's pretty straightforward. Hopefully, this all look reasonable to you. Good? Okay, cool. So in the microcontrollers we actually also have this data alignment. You're able to set where this data is going to be aligned with each other. You can put it to the right alignment or left alignment. The reason for this is mainly so that become more like flexible. Depends on how you use this register. Because remember, like all these registers are 16-bit, right? And the highest resolution you can go for this ADCs are 12-bit. So naturally, there is going to be some bits that's unused. And if you set it to be even like a lower resolution, 8-bit, etc., then you have more of these bits to be essentially, hanging there, floating there. So you have the options of just how you align with them. Depends on how you want to do like the bitwise operations, for example, or how you want to just align them. The ones that you can also use some of them as the sign extension. So anything that's before that, for example, if we look at like this one, the top, like the 6-bit one, the sign extension bits, it will take up 8-bit, and those will be essentially the same value. So if it's negative, it's just going to be all ones. If it's positive, it's going to be all zeros. I know that usually only take 1 bit to determine the sign, but you have multiple of these bits there, and it doesn't make sense to just padding 1 bit instead of having them all consistent with each other. So yeah, however you choose it, if you have like a sign signal, the amount of the bits in front of it, they will all be that sign value instead of just a bit after. Yeah.
What is an injected channel? I see like
Great question. So we will talk about that in next slide. So the regular channel and injection channel. So good catch. So basically, the regular channel, as the name indicates, it's the main sequence or like the main queue of the ADC channel. That's like the default ones that will be used, and it's pretty straightforward. It goes in, and then it goes to like a regular data register, and then goes to however the APP buses, etc. The injected, it's a higher priority queue. So essentially, you can use this to, in a way, interrupt the regular ADCs. It basically have like a separate set of hardwares, and it got its own data registers. So the data between the regular and the captured data between the regular and injected ADCs, they will not conflict with each other because they don't share the same data register. Usually the injected one is just have like a higher priority than the regular ones. Some of the commonly used cases for the injected ones will be, say you have some reading that needs to happen at specific time, and maybe they're not periodic, right? So you actually use one of the timers to track that, and whenever that happens, it interrupts the current ADC sampling sequence and does that, and then go back to the main sequence. Yeah, does that? Yep.
I just wanted to clarify. So, like the regular channels are just what we typically use for just like reading data into the DAC, and then the injected channels have like a higher priority compared to.
Yes. So this is still under ADC. So yeah. So the data will goes the normal read will goes to the regular channel, and the injected channel, you will be the one who set it. So it will have a higher priority. It's quite common that, so we will see here, let me just give one more slide later. In ADC, we have different modes. If we only look at whether it's one start and stop or start and then kind of like loop there. So largely speaking, we have like, one single sampling, and then we have also like a scan mode. Basically means you continuously sampling. So for the continuous sampling ones, it's pretty much going to be the regular channel, usually. Yeah. For the more, whenever there is another higher priority or any interrupts or sensor readings that needs to happen at a very specific time, then that's when the injected channel comes in. And while we on top of this, you can also see that there are this single channels. Like the two mode has the you could do it with only one channel of the ADC, or you can do it with multiple channels. Remember, like you have more than one channels, ADC channels on your device, right? Actually, you have 16 external channels, right? So what this would do is you can have them programmed to be in sequence. So, like for example, I guess a common example for this one, maybe you're driving your car and the car does like one of the scan of the sensors on the car every, I don't know, 5 minutes or something. Tire pressures, the engine oil, temperature, the various numbers of these things to check in a sequence. So that would be what this type of scan mode would do. So it would have them listed in sequence, and then you sample those channels one by one. And for these ones are just, you have that one value you care about in your system. And you either do it once or you do it continuously. Depends on whether that data is needed like periodically or if that data is only need once. Does this sound good? The need once one type, it can, it happens. Sometimes it's more common. Well, it's not more common. I think they're equally common. But if you had to use the injected channel on one of these cases, the one time is the more commonly placed to use the injected channel. But you can also just use the normal regular channel for that. There's no issue with that. Yes?
So these channels, can they be either regular or injected, or are they always regular ones and then the injected ones just go in addition to that?
For these two, they can be like either. So for these ones, if it's labeled as a sequence, then it's typically regular ones. Or if you program it's either regular one that happens periodically, or if you programmed these, say, 4 injected channels that happens in sequence, that's also possible. Depends on your own configuration. But if you do the injected channel, depends on how you configure it, the order of it when it happens might vary. But for the regular ones, the order would just be however the default order is. Sounds good? Okay. So another thing to keep in mind is that the V reference, most of the times, or most of the examples you see so far, in order to use, we try to like change the signal gain before it reaches the ADC channel, right? We usually set the ADC channel's range to be just ground to VCC or VDD, depends on how you connect it. But it's also possible to just set a different value as the reference. It does not necessarily have to be the VCC of your system. It can also be a separate value, for example, half of that value if you have a voltage divider circuit somewhere. So this is also quite commonly. So you can also just essentially change the range of the ADC in order to maximize the sampling range, sampling bit of that. Does that make sense? Did I explain that right? So for example, if you have like a 0 to 1, if you have an input signal that ranges from, say, 0 to 1 volt, right? One thing you could do is you can have like a gain control of this input signal and then amplify it to 0 to 3. And then that goes to a ADC channel, say 10-bit ADC channel, that ranges from 0 to 3.3 volt, which is the VCC that's being used for the V reference. So that will give you maximum, or like a optimized, really optimized range of your ADC bit. The 10-bit value will mostly all be used. So you have like essentially a higher resolution signal, right? You could also do, just keep this 0 to 1 signal, directly let it go into the ADC, but set the ADC's reference to be, say, 1.1 volt or something. And then this will have essentially the similar effect as the other way, so that you can use the entire 10-bit within the range of that. So this is essentially just tell you, you can change how you would optimize your ADC sampling at various points on the whole sampling sequence. Was that more clear? Any questions? Okay, cool. And here is the watchdog. This would be like a pretty standard examples. So we have like a area, and then we have a high threshold and low threshold. What this is usually it's like a hardware threshold monitoring. This analog watchdog will continuously check the ADC conversion result and at a very, very low power consumption, and raises a flag or interruption if the measured value is either go outside of this guarded area or go into this guarded area. Depends on how you set it. And this can be done on like hardware level. And you can imagine this be very, very useful for the embedded systems that run for a long time, but you don't have to have it working all the time. So you just put it in sleep mode for most of the time, and whenever there is a trigger signal coming from the ADC channel, that became like a wake up for the entire system to do something. Yeah.
For the previous slide, I understood that like VREF is not necessarily VDD, but how do we actually infer it then?
What do you mean, how do you infer it?
It says, how would you infer the internal VREF?
Infer the internal. Oh, it depends on how you just need to know what's the value, because they have a few internal values that you can choose from. Just choose the right one, or you build your own ones. Yeah. Just make sure you know what is the V reference stands for. Oftentimes it is VCC, but it doesn't necessarily have to be. Okay, cool. So this would be like from like a higher like if we zoom out a little bit. So basically you have something happening on like a peripherals, and there is an interrupt happens. The ADC peripherals will use it's being called to do this sampling, and this is one way to do this. Essentially, the interrupt goes to the ADC. The ADC sends back a the ADC is being initialized, essentially, the flag that, I'm working on it, and then go back to the main program. And it's let each ADC channels to do the interrupt. Remember, each of these external ADCs, it has its own, internal interrupts that can be triggered whenever they have a value coming in. And this is one way to do this. You can also do what they called this like a less amount of interrupt ways. So essentially, instead of having that down flag coming from the ADC peripherals, you can also use the DMA, direct memory access, to just have those sampling channels value to go into the DMA. And then the controller will be the one to send out that one flag indicating the entire process, or entire process is done, or periodic. If it's a periodic execution, then this time it's been done. Different ways of implement it. Usually this way will save some of the hassles on the code level because it has less interrupts. But there's also nothing really wrong with this implementation if it's just a quick read from one sensor modules instead of like a periodic reading. Looks good for the ADCs. Any questions regarding ADCs so far? Yeah.
I'm sorry, what is a DMA?
Direct memory access. So essentially, you can access the memory space without going through the CPU or the core. Yeah. Any other questions? All right. So today we're going to move on to the remaining part. We're going to talk about the DAC, the DAC, digital to analog converters. We're first going to talk about different types of DACs, just as we talked about ADCs, and then we talk about the ones we have on board and some of the error types we have and how we could potentially deal with them. Again, some reading materials from the reference manual as well as the textbook. What would be a good example of a DAC in real life? From the electronic workshop perspective, it will be this device. It's called a signal generator. Have you used this already or not yet? Okay, I see a lot of nodding heads, so I assume you guys are very familiar with this. And we can also, if from like a more daily usage, the speaker will be a perfect example of a large piece of a DAC. Essentially, it takes whatever the waves that's being generated from your microcontrollers or from your computers, and then take that analog output, converted analog output, into a sound that human can enjoy. And similarly to the ADCs, they also have this conversion process, essentially converting the digital data into a voltage by a n-bit DAC. It's pretty much similar to the ADC. You have a V reference, and then depends on how many bits you have on the DAC. You just divided that's the amount of steps you have, and then it depends on the digital values. You divided that to the steps to find out where in that ladder your value is, and then times that with the V reference, and that gives a output on the voltage level. So this will be a very simple example. This is only 4-bit, so the output signal is likely not going to be this smooth. It's going to be a little bit stepped, if you think about it. But with more bit added to the DAC, the smoother the entire wave will look like. But also depends on the frequency of the signal you're actually outputting. So, does this?
Why are we subtracting 1 from the digital value? Because isn't a digital value of 0 indicating 0 voltage, but then that would be -1 over 4096?
That's a good question. So yeah. Again, let's not talk too much about this +1 or -1 thing. Chances are it's going to be taken care of. In this particular case, it probably means for this microcontrollers, the digital value is ranging from 1 to 2 to the n or something like that. So depends on number of steps you have. You have to kind of ignore either, in this case, either the 0 or the top voltage. So between these, they chose to ignore the top one. So the digital value the actual output will never really reach the V reference. It will always be a little bit one step away from it, but it achieves the 0 output. Yep. But in real life, it shouldn't matter that much to the real life. Any other questions? Okay, cool. So before we dive into how exactly this DAC works on the hardware level, let's first introduce a concept of loading effect. So loading effects is when the output of the DAC is connected to a load, a resistor, capacitors, or like an active circuit, etc. And this loading, these loads will typically drive some currents from the DAC. So that will affect the DAC's performance. How this will be like a very, very easy example. So basically you have the V out here that will be connected to just a resistor, a load resistor. And based on this voltage divider equations that I hope you guys are super familiar with by now, you will see that the V out will be actually affected by the number on this our load, which, if you think about it, which is really not great, right? Because we don't really know what's your DAC channel going to connect it to. It could be connected to just a single wire, or it can be connected to a big piece of speakers that your device can't push to make it sound, right? So how do we make sure, or at least how do we reduce this effect to try to push this the V out to stay consistent? Depends on the various of the load that you might connect to the circuits. So one of the easy way, or like a pretty standard ways to do, is to add an op amp. So this is essentially a voltage follower circuit that it will try its best to keep that V out to be the same as the V in that connected to the positive side of the op amp, and that helps you to have roughly like a V out roughly equals to the whatever you're trying to achieve as your system desires to be. And we have actually a circuit built for you to show you the difference. Okay, so let's say this is just like a load, like a normal naive DAC output, and the R source, the source register is say 100 ohm. This is something that you typically can't change because it's just some internal resistance from your systems. And this currently is 1K, which is not too bad, right? We reach, what's the value? 4.5 out of the desired value 5 here. But if you change this to say, let's see if I can do it here. You will see that the output value will drop dramatically. This is just the voltage divider effect. But if we have like a voltage follower, then you can really it's still going to stay at the 5 volt. Obviously, this is a super ideal situation because this circuit is simulated. But in real life, within the operating range of this op amp, you should be able to have a relatively consistent output from the other side of the op amp as a voltage follower. So always check the data sheet. But if these things are typically handled internal for you. Any questions regarding the loading effect and how we, yeah?
Why does the configuration even allow a buffered and an unbuffered mode when it seems like the buffered mode offers no downsides? Why not just always use it?
You mean the first, like why would we even have this?
Yeah, exactly.
Yeah, we don't. This is just like a naive approach that,
well, I guess,
yeah.
I just from what I remember from configuring the actual DAC in the STM32 alpha as an unbuffered mode.
If I remember correctly, this op amp is already integrated inside of the DAC channels on the STM32. I can double check, but I think this is already inside of the DAC. I don't think you need to add a, unless it's out of the range. But I'll double check on that. Yeah, but that's also one thing. So if you see, like you will see on either ADCs or DAC, you will see the operating range of that. That typically means outside of what if the output load that's been connected to is larger than that amount or smaller than that amount, that means whatever circuit they have inside will not operate correctly. So even if you add this voltage follower, it doesn't solve the word. It just gives you a relatively consistent output within a designed range of that hardware component. It doesn't solve everything. Any other questions regarding this? The load effect? You can think of it like kind of like one of the, I guess, sample and hold circuit, but in terms of a like a DACs perspective. Okay, so then we will move on to the one types, and actually one of the simplest types of the DAC. It's called PWM filter. You guys probably remember, you have like a RC circuit, and then if you have like a consistent voltage, then it takes some amount of time for the RC circuit to charge up, right? So depends on the amount of the value you put on there, the charged up value will be different. And conveniently, we could use a PWM signal to generate a effectively different level of equilibrium voltage signal. Depends on how long, essentially, the duty cycle, what's the duty cycle you set based on your PWM output. And that can be conveniently used to convert a sine wave look-like signals. For now, we will just talk about single frequency signals to make it simple. Of course, in real life, the actual signal will not be that smooth. You will typically see this kind of spikes that throughout this type of operation. But if your application does not care too much about the performance, this will usually do. So why you see this spikes instead of the entire thing is because this type of DAC also is a PWM signal. It passes through like a low pass filter. So only the rapid on and off shifts of the PWM signals is being kept there. The remaining part of that signal is being just cut off from the output. So you have essentially a value that's corresponding to the PWM duty cycle you set at that moment. And you will have like a signal generated like this. We also have a circuit that we put it out. So if we have, say, if I change this duty cycle, right? You can change the value of what's the stabilized value of this circuit. And if I change it rapid enough, and then, I can just generate this. Okay, I'm not doing it really well, but let's make the speed way up. And so, something like this. Does this look good to everyone? How this type of DAC signal is generated? Essentially, just essentially a PWM signal that corresponding to a value and then connected to a low pass filter to ensure only the value that corresponding to that that you want is able to enter the output pin. So you have this kind of zigzag shape of output. This was this obviously is like a zoomed in version. In the actual wave, it will look reasonably okay. Depends on how fast or how you set your PWM signal. The faster it is, the smoother it is. Yeah.
The point of the PWM, the circuit as a whole, is just to use the DAC to create a sine wave in an analog form?
Yes. So we're using the sine wave as like a representation of what a analog signal would look like. Because a sine wave would be like I guess most simple. It's just like a one frequency signal. Obviously, in real life, it would be a lot of signals that laid on top of each other. But the idea is the same. You have at each point you have a value that the DAC needs to produce, and this is how that value is produced at that time. We good on this? Any potential downside you can think of this, except for the fact that it doesn't look perfect? Just think of like, for PWM signal, it takes some time for your PWM signal to generate, right? You have the period needs to be set. You have the duty cycle. That means each of this PWM signal will take various amount of cycles to generate. And that on top of the actual charging time you need for this RC circuit, that's additional time added to it. So you can almost think, this type of DAC will not be capable of generating something super fast, at least outputting a desired analog at a very, very high resolution, so to speak, because it just takes a lot of cycles to produce one valid output. Yeah.
Is the slight distortion in the output also going to be obviously not ideal because you might
Yes, exactly. So if you are one of the folks who are like hi-fi fans, this will not be ideal. I'm not sure if your ear can actually tell, but it's not ideal. Okay, so the second one will be the resistance voltage divider, or I guess it will be a couple that uses similar idea. But this is essentially one of the simple version of this, or like one variation of this. Remember like the flash ADCs we introduced before? So on that one, you have all of the same value of the voltage that divided each of the steps between 0 and the reference, and then you essentially compare the input voltage to whatever values this voltage divider can generate, and then decide on an ADC input value, right? Similar idea can be just adapt on the DAC as well. You have, in this case, 3-bit, so you have 8 steps of possible output steps of like possible voltage output steps, and then depends on what's the value you need to generate. You just switch on and off. This will be like super fast switch. It's not going to be these, but just as the indicator of the switch, and then that will be just go through like a voltage follower circuit to be used as a Vout. And typically, we will use like a decoder to control the input for all these switches. So you only need like 3-bit to control this entire piece of hardware. And one of the obvious advantage of this one, as you will imagine, is it's super fast. Although it looks like it have a lot of these switches, but all of them can be just configured. You can essentially think of the entire process of a value coming out of the circuit is pretty much one cycle. So one clock cycle, you have a value. But obviously, it depends on how many bits you set it to control this type of DAC. The resolution of your output is dependent on that. We actually also have a circuit built for this, but this is pretty straightforward, so I would not bother to open this. Essentially, by shifts between these, you have a output on each of these steps. You're able to have output of each of these steps from the Vout perspective. Anyone have any questions regarding this type of resistance voltage divider DAC? And any disadvantage you could think of on this type of configurations? Yeah.
Will it get very costly to have all those resistors if you want a high resolution?
Yes, it will get costly. So based on the both on the component wise and also on the space. Typically this will be done on the IC chip because it's just unimaginable to do it on like a PCB or something. So that helps with the space, but still, with all these actual components cost, it will still take up like more space than usually needed for other type of DACs. Any other thoughts? Yeah, I think that's mainly that. Also, it's just not very scalable, because of the space it has and the amount of resolutions. So the time resolution will be very high for this one, but the actual voltage resolution of your output voltage is quite limited based on the amount of components you're willing to throw onto this configuration. So it essentially increased to like 2 to the n, which, not ideal, but works. So based on that, we had some variants based on the idea of the voltage divider. So if we are able to like turn on 2 switch at the same time, then we could potentially share some of the resistors that we used in the previous configuration, right? So we actually have this type of, you can think of this like a building block, like a summing amplifier circuit. So essentially, this is the formula you can use. Basically, what it does is gives the same amount of same bit resolution of the output resistance, output voltage, but then we can reduce the number of resistors by quite a lot. And this is basically done through the RF on the top, and then you just compare with the Rin. The Rin here, if they are the same value often, then the whole formula can just simplify it as this. So it just depends on how many of them are connected. You have a choice of a step for all of these levels. This can be served as a building block. So that will lead to this configuration. So like a R and 2R. You will notice that the 2R and R, they purposefully chose this so that it's easier for the it's easier for the manufacturing. So you could even do like just like 2 Rs, 2 of the R resistors in sequence. So it would be much easier to, in terms of the fabrication and manufacturing perspective, much easier to do like a R, 2R, 4R, etc., rather than if we have a R and you do like a 2.2R or 4.7R, etc. And it's similar idea. It's essentially like a fancier voltage divider and uses less amount of resistors for this. I think we had, do we have a, let's see if we have a, oops, yeah, I didn't have that put out. So on top, oh, sorry. Yeah. Based on the similar idea, we also have another variant version of this voltage dividing circuit. And then you can call this binary weighted. So instead of having the R, 2R, we have essentially a V reference connected to the circuit, and you have the R over 2, R over 4, R over 8. And then that also depends on which of these shifts are connected to the circuit. That will give you a continuous value for all the 4-bit steps. I think hopefully this is pretty straightforward. It just depends on which one you close on that switch. Then it gives you a voltage value, and then all of them get added up to the circuit and then being used as the output. Does the binary weighted resistor DAC looks good to everyone? All the ones that have been using the voltage divider or using that concept are all very, very fast, essentially. All these can be producing that output under 1 clock cycle, essentially. Because similar to before, this switch control thing, it's just 1 clock cycle, and after that, the voltage output is ready for you. Obviously, you can use, it's essentially the same if you do like R, 2R, 4R, 8R. It's just however you define your Rs. But usually it's in these binary ratios. It's, again, like we said, it's going to be mainly for the manufacturing consideration. It's going to make it easier, but still, it's going to be much harder than just use the same exact the Rs. And this type of DACs, you do have to have very accurate, very precise resistor for it. Yeah.
Is this still relying on the like summing amplifier circuit?
It's like a variant to this, so they essentially work on the similar principles. Okay. Yeah. And on top of the, yeah, I can. So why it would be harder to do, why it would be much harder to do like you know, R, 2R, 4R versus just do Rs is because if you manufacture everything in one batch, it's easier to get them similar to each other. For example, if this 1K resistor you manufactured, but it's actually 995, which is pretty okay, then chances are that entire batch are the same 995 or very, very close to 995. So as long as you use the same batch of the resistors, even though the actual value is slightly variance, you can still have a very precise like voltage divider. Like if we go with the most OG design of the DAC, you can still have a very precise version of this. Although each R might not be exactly the value you wanted. However, for the ones that have more complicated ones, for example, these ones, chances are they will be fabricated at different batches. So any of the little variants can add up to these type of configurations. But again, this reduces the amount of the resistors you need by a margin. So trade-offs. And another thing to realize is that, to just keep that in mind, is that similar to the ADCs, all these outputs from the DAC is also kind of have this zigzag, like step kind of shape. Just depends on how many bits you put onto this DAC. Okay. Any questions for I guess the few types of DACs that we showed? 4 types, but the latter 3 are working similar principles. Great. So let's look at this one, and let's spend maybe 5 minutes, 5 to 10 minutes, 5 minutes-ish, and talk with your neighbors, try to figure this out, and then we can look at it all together. So just the 4 different types of DACs we have, and then if you have to give it a description or a ranking for the resolutions, for the speed, for the linearity, and power, number of resistors, etc. Okay, let's talk with neighbors. All right, let's look at it together. A little bit clarification on the linearity. It basically means how consistent the value changes is between each steps. For example, how consistent or how consistent is if the digital value is increased from 001 to 010, what's the value of that amount of increase in the output voltage compared to, say, the value from 010 to 011. Essentially, how accurate each of these steps are. All right, let's look at the resolution first. This is given the same amount of areas you can work with. Which one has the highest resolution? Anyone? Or which one have the lowest resolution? Yes?
You said that the PWM one would have the highest resolution because you can give it like any PWM cycle.
And then
And then for lowest, we said voltage divider because it's like the most expensive in terms of resistors.
in terms of the areas per, and for the latter two will be median. Yeah, I think it's except for the PWM, but PWM. So we labeled the PWM as median, but with a star because it's kind of based on time, but not based on the area. So it's kind of hard to really give it an accurate ranking here. But on these three, the latter two are it's going to be much closer. So it's just because the amount of resistors are used, I think, for the R and 2R ladder compared to the binary, it's about twice amount of the resistor needed for the same bits value. But yeah, they're just a constant difference, so it's not too bad. So, anyone disagree on this? Any questions regarding the resolution part? Speaking of which, I think like when I was walking around, I think there was some confusion about like how are these values being selected. So if you just remember how the parallel resistor got added together, the 2R and 2R added here became an R, and then the R and this R, they became divided everything in half. So essentially at each of these spots, everything down added up to be an 1R, and then that divided whatever current flow through by half. So essentially, each of the points was dividing by half. Hope that's so. Everything underneath added up together to the top would be 2R, and then that divides everything by 2 from the very top. So this is just like why they said it this way, so that they all not like very convenient. It became divided by half, divided by half, divided by half, divided by half. Okay. So how about speed? Which one is fastest? Which one is the slow one? I think we talked about this. So the latter three are essentially just one cycle. So it's pretty fast. And the first one, the PWM, because it takes various cycles to generate the desired PWM, and then the RC charging time, and a few here, a few there. So these add up to be going to be like the slowest of all, and it's going to be very slow compared to the other three because it needs so much more clock cycles to do. The linearity, how about that? How consistent is each of the steps within that DAC? How accurate that step is? Any guesses? Who has the highest linearity? Nobody? Who has the worst? Yeah.
Would it maybe be the voltage? Well, actually, I don't know. I was thinking the voltage divider might have lower linearity because there's the error of each resistor compounds.
The voltage divider or which one?
The voltage divider, because like if you have the variance in resistors, wouldn't it compound as you chain a bunch of them together?
Yes, it would, but like normally they would just use the register that fabricated in one batch. So even if that value is not super accurate, the whole batch would be not super accurate. So they essentially have very similar values. But yeah, I think that's the right angle to think about this. So it essentially depends on how easy to build from like a manufacturer's perspective, and for the latter three. The R and 2R, because it's going to be still median. You're only using two values. So that error ratio will essentially be how close are this batch of R's compared to this batch of 2R's, right? For this one, it's just usually quite consistent because you use the same batch. And this one will be a bit more trickier than the R2R ladder because you have more than just more than two values to consider. You have 2 to the n amount of values to consider, depending on how many bits you want. And for the linearity for the PWM, it's going to be, a little bit low. You can see from all the zigzags and the signal generated. So. The power consumption. Anyone? Okay, I will just give out the answer here. The PWM is actually quite low because one thing that the microcontrollers and computers are doing really well and really fast and really cheap in terms of the power is counting cycles. So there you go. And the voltage dividers or like voltage divider based DACs, they are all like on the median side. You just have a bunch of hardware components connected to it. And if you had to distinguish between them, I think just because the voltage divider has more components and more switches, it might have slightly higher. But the total amount of the resistance that that current takes should be quite similar between these. How about the number of resistors and switches? So this is, we're expecting like a number to put here. Obviously, we don't have any resistors or switches needed. Well, we have one resistor needed for this, but that's pretty minimal. How many resistors and how many switches we needed for the voltage divider for a n-bit DAC using this? Anyone? It's going to be 2 to the n because you essentially just convert your how many bit n-bit decoder into one resistor per bit. So 2 to the n for both switch and resistors. For the R2R, how many would that be? Yeah. Yes, pretty much. It's 2n plus 1 because there's like 1 down there. But yeah, so roughly 2n. And then n amount of resistors because each one corresponding to essentially 1 bit of the DAC output. How about the binary weighted? How many? So because it has the predefined value, so this one actually needs n plus 1 resistor. The plus 1 is the R reference that's connected to the op amp. So there you go. Very lowest, just 1 extra resistor for the RC, and 2 to the n, 2 times n, and n plus 1. Yep. Any questions regarding these? Okay, cool. The answers will be posted in the slides after the class. So these are the DACs we have on our STM32. We have 2 of these output channels. We have 8-bit or 12-bit output mode. We have the buffer shift calibration. We will talk a little bit about this on what they actually means. We have the synchronized update capabilities, and similar as the ADC, you can choose however you want the data to be aligned with. And we have the sample and hold mode. Just again similar to the ADCs. And the types of error or like common errors that in ADCs and DACs, We have the common ones we will introduce. First is the quantization arrow. We talk about this in the DACs. Basically, you can think of them as like the least significant bit that's like noise or uncertain. This is just, this is like based on the hardware limitations because you need to output one value, right? And anything between that range of the lowest significant bit, it can go either way, depending on how you set it. You can set it to be the middle, or floor, or yeah, seal, however you set it. But in that amount of range, you're gonna have a like a quantization error that you cannot fix. We also have what they call offset arrows. This is in a DAC. It was the like essentially the deviation of the actual output value from the expected output voltage value. And this like for example like the digital value is 0, depends on how you shift the actual output voltage. You might have the the lowest. You might have that value corresponding to 0 or like a small voltage number. This is similar to, I think one of the class member mentioned, if you want to -1 or don't -1. These are essentially a offset value. But this is something that you can usually easy to calibrate. And actually the STM is doing this for you. So you just you can have like a so based on the internal setup, this type of error is usually handled by the STM. So essentially, there is like a 1/2 last bit shift included in the actual output. So it might just depend on it might just add it 1/2 steps to all the output voltage to minimize this offset error. We also have this gain arrows. This is when the actual output from the DAC and the desired output shifts or varies, but proportionally to the amount of bits you added to it. So it's essentially for like the DAC's perspective. You can think of it as like the output voltage increase at a wrong rate compared to the digital input for the DAC, but they are proportional. So these things are also kind of easy error to like calibrate. Basically, what it does is you can just sample a bunch of known values or like the output DC values that are pretty accurate, and you can use you can just implement like a easy transfer functions to calibrate this out. So this is also one of the errors on the hardware that could happen, but usually pretty easy to calibrate. We also have a differential nonlinearity. So this is a little bit trickier. So it basically means that it can be it's like each of the step sizes. It can have a little bit value shift on both directions. So this if this value is relatively small, then maybe it's okay. We can show you different cases. The worst case you could happen is that variance between each step actually might go beyond your step size. So essentially, you have, let's say you have a very high number of bit DAC, and then between the 00001 and 00010, the small difference between them is actually smaller than this type of arrow on each of the bits. So that might actually go over to the previous, which is, this type of error would be pretty hard to calibrate because, with like known values, it could go, essentially the range could go to more than one steps. So this type is going to be harder to do. But I don't think we were required to actually debug these type of circuits. Just be aware that these type of errors could exist in the actual DACs and ADCs out there. Just a lot of hardware is putting together, all the simulations and all the types of DACs or ADCs we introduce are all in almost like a perfect physics world, but in reality, depends on the range or depends on the manufacturing. These are all the errors that can be included. We also have the integral nonlinearity. It's the maximum deviation of the actual DAC output from an ideal straight line response. So if you draw a line and depends on how you fit this line to your steps, this arrow is essentially what's the distance between that line and your step. What's your step needed? Again, these things, ideal situation, you could just convert the digital value and then so that it can be proportionally to the analog values if it has a very consistent integral nonlinearity error rate. So basically, if we just to give a quick summary on this, we have the absolute arrows. We can have off scale, full scales, like the let me check. Integral nonlinearity, the difference nonlinearity, all these type of errors that could happen in the actual hardware. You don't have to worry too much about debugging them, I think, but just be aware that you need to know this. And how do you know all these is going to be in the data sheet of that actual hardware. So read data sheet as usual, and then make sure that whatever use case you used it for is within the measurement range or within the intended accuracy of that. Typically on a DAC or ADC, you will see that there is a plus or minus sign somewhere, either in dB or in voltage proportional to the reference. That's essentially the accuracy of that piece of hardware. Usually, as long as you make sure your data is that amount of small variant of the signal will not cause any misfunction of your system, then you're good with that piece of hardware. So yeah, errors can happen and they always be there. Some of them we can calibrate, some of them we can't. Just make sure you chose the right hardware. Okay, so just this is a quick recap of the lecture. If you have